10. So, say it again.
How are we supposed to find out the maximum number of infections that could occur in any given Is it from looking at all the iterations?
Right.
Okay.
Right. So the question was in problem number 5 in this homework, which refers to problem number 10 in chapter 4, part B. It says estimate the maximum number of new cases in any 1 week. So the new cases is infected, right? So it's basically looking at the infected population over the span of that week. Hold on, in any 1 week.
So that'd be like looking at all the different iterations of the disease. But there's like 17.
Right, because this is a weekly thing, right? It's an updated weekly, is that?
Yeah.
Okay. Right. Okay. So it'll be the maximum of all the iterations. I mean, all the values in.
Maximum infected people.
Right.
But does that imply necessarily that they were infected that week?
But if you subtract out prior week, you'll have the
Oh, new cases. So right.
new
So,
cases. If you subtract out the prior weeks,
so the difference, the delta I, whatever.
the delta for each week.
Not necessarily, because then you're also losing the people from the week from 3 weeks back.
You got to add in the people that became immune. Because you're solving the
Right. Well, I mean, at each iteration, you can count how many new cases there are.
Yeah.
You know, is the number of infected. Let's see. I don't remember the
New
exact.
infected minus the last week's infected.
So I is the number of infected. C is the number of immune, right?
You didn't want us to use those formulas you gave us.
Yeah. By the way, that model is kind of not a famous, but I mean it's kind of the original models for this kind of infectious disease population. So. Right, so how do you account for the new cases? Count the number of infected that week, subtract the number of infected the previous week.
And if you save the previous week's information before you overwrite it, then you'll have a delta on a per week basis.
I was thinking the delta, the positive term on your delta I should be the number of mixes that you gave us.
A S times I?
Yeah.
That's the rate. Okay. Because then it subtracted the number of immune cases, the change in the number of immunized people. So. So I guess it makes sense to look at that rate, A times S times I, right? So S times I, the product of S times I. All right. Let's see. Any other questions? Yeah, it doesn't help that I actually skipped assigning this problem back in chapter 4. I should have assigned the problem in chapter 4, so then it would have been much easier, I guess. But all right, so let me say one thing. So there isn't really anything new in chapter 6 that we need to cover for you to work on the other 4 problems, I believe. One of them involves, so let's see, it's 20, 21, 25, and 26. So number 21 actually is ask for an implementing of the Runge-Kutta method. And notice that there isn't much. Well, so this is just an exercise in modifying that code for the, instead of one line, you got to put 4 or 5 lines. But also what I'd like to point is, you remember how in Euler's method we look at kind of how things change if the step size h changes, right? If it gets smaller or if it gets larger, right? So one way it's kind of you're approximating the true dynamics of a continuous system. If you make h smaller, if you make h larger, of course you're going away from the continuous system, and in turn you get this chaotic, sometimes this chaotic behavior, right? Period doubling and all this. So I guess it's the same question that could be posed for the other methods like Runge-Kutta method, right? So if h is instead of made smaller and smaller to get a better approximation for the continuous dynamical system, what happens as you make h larger? I don't know if there's any particular question for you to do that, but if you're curious, I think you could take any of the other problems, and instead of implementing Euler's method, implement the Runge-Kutta and increase the h value. Of course, you're going to see different things than you see when you use Euler's method, but you will still see chaotic behavior no matter what. So try. I mean, again, you can try them even now, and let me know by Wednesday if there are any issues with those problems. Okay. Also, so on Wednesday I'd like to, or even today, I think if time permits, I'd like to start talking about Chapter 7. Which takes us in the realm of probability models. And basically stay with it sort of to the rest of the semester, except possibly move to, certainly talk about Markov chains, which is a type of discrete dynamical system that has probability kind of, it's a probabilistic model. But, so the nature of Chapter 7 is that it's just sort of a review or sort of a rephrasing of things that you should have seen in other courses, and how they kind of fit with what we've been talking about. So before we start with Chapter 7, I'd still like to talk about some of this chaotic behavior that is seen. We've seen, certainly we've seen it in discrete dynamical systems. And also I mentioned in continuous dynamical systems there are, very relatively simple physical systems where this kind of sensitive dependence on initial condition is observed. With this, I want to emphasize the fact that we don't have, in all these models, there's nothing probabilistic. So there isn't, these models sort of ignore anything that's random. Okay? So even in this Lorentz model for, let's say weather prediction or weather so it's basically three variables that are being observed in let's say the portion of the atmosphere, and these variables represent, let's say one of them says represents the rate at which convection rolls rotate. Y represents the temperature difference between ascending and descending air currents, and Z represents deviation from linearity of the vertical temperature profile. So so again, it's not exactly what I was saying last time, that you talk about pressure, temperature, and humidity. Okay, but the striking feature of this model is that how easy it is to write it down, and it basically, I'm going to use X, Y, and Z since I think last time we saw it like that. So it consists of terms that are simply either linear or quadratic, right? So it's like predator, prey type terms, right? And there's absolutely nothing so this is a deterministic model. Right? So no random effects are observed, or even if there are in the model, I mean they are ignored. And we're just simply saying that at time 0 the x of 0, y of 0, z of 0 are known or are given, and then this dynamical system is deterministically projecting what the variables x, y, and z will do, right? Still, what I said last time is that it's done deterministically, but it is very sensitive to the values of this thing. So for practical purposes, even if this cannot be known as exact values, right? So there is some, you wouldn't call that random, or it's not, this model is not supposed to take into account any random fluctuations of that initial condition. Okay? It's just simply to solve these differential equations and tell you the behavior of the system. And let's see, so last time we had this, and it's not p-plane, of course, right? Okay, so I think it should be the same system. Well, some of the parameters are renamed, right? Like this is, instead of A should be sigma, instead of B should be R, instead of R should be B. So these are kind of flipped around. Okay, so maybe I'll change them just so we can. A is sigma, looks like sigma, so I'm going to leave it like that. Okay, so, and we remember that's sort of this dynamics. Okay, so what do you do with every system? Well, with every dynamical system, what have we been doing with every dynamical system like this? The first thing you do, you do a steady state analysis, and of course you study the stability of the equilibria, right? So this is simply a system of algebraic equations. Okay, many of them, some of them are even linear, 0, which you can actually do it explicitly by hand. Okay, although it's, you run into that risk that it's not going to give you anything but it's actually written down in the book of the steps there are. So there are actually 3 equilibria.
Ready?
Yep.
On your second equation, they wrote Rx instead of positive.
Thank you. This is what I have here too.
Yeah.
Yeah, thank you. Okay, so again, this should not be an exercise in solving a system by hand, because it's a nonlinear system. So, but you can see. I mean, x and y seems to be well, and also I have a plus here, right? Okay. So in fact, x looks like it has to be the same as y, and then you have these 2 equations which you can solve for x, y, and z. So the one equilibrium is obvious, is 0, 0, 0, and there are these 2 other equilibria which I think differ just by, well, slightly. So this is b r minus square root of b r minus 1 square root of b r minus 1, so that's x equals y, and that's z, right? And there's a minus, which would just then have a minus here. Okay. So in the xyz xyz in the space, you have this. This is one equilibrium, and then there are 2 other equilibria. One it's let's see. One it should be kind of in the first octant. Let's see. R, I believe it's chosen to be 28, so that is certainly positive, right? Oh, excuse me, greater than 1. Okay, so it would be something like this, and then sort of the symmetric with respect to the z-axis, or not? Yeah. Okay. So kind of it's, if this is the projection of the xy plane, then these 2 things are kind of mirror images. Okay, with respect to the z-axis. Okay, so you have 3 equilibria. Now, there's no p-plane, there's no phase plane here, right? It's phase space, and then it's difficult to say anything about the solutions. So what you do is the next thing to do is to study stability, right? So the stability, I mean, simply amounts to do what? Linearizing around each equilibrium, and so remember, for continuous time dynamical system, that's amounts to computing the Jacobian metrics, right? In this case is minus sigma 0 r minus z minus, why is that minus 1 there? Oh yeah, because it's minus x minus y. Okay, and then it's minus x. What's the last one? Y, x, and minus b. Okay, so this is just taking partial derivatives. Okay, so it's a 3x3 matrix. And you can certainly do this symbolically, right, or whichever way you want. If it gets too complicated, for x, y, and z equals 0, this is relatively easy, right? But for the others, it's going to be kind of hairy to find the eigenvalues, right? But you need the eigenvalues of this. So at 0, 0, 0. Let's see, the matrix A has 3 eigenvalues, which are lambda 1, lambda 2, that's minus 11 minus square root of. By the way, these values appear. The reason for these numbers is because of the choice of sigma, r, and b. Okay, so I'm not actually writing. Well, I guess we should try to see what the eigenvalues look in terms of sigma r and b. But if you don't have any kind of choice of sigma, let's see. I'm sorry. So I think this is kind of a sensitivity with respect to one of them, the r, right? So for the sigma and b, there are values that are being kind of fixed, right? So the point is that you want to kind of choose one of the parameters and make a discussion based on the possible values for that parameter. So you have to choose the other ones, right? Otherwise, it would be kind of difficult to make any conclusions if you had sigma and b and r in this eigenvalues. Okay, so what do we look when we compute the eigenvalues for this Jacobian matrix? We look whether they are positive or real part is positive or negative, right? So let's see. I think well, certainly this, if r is a positive number, this is real, right? And this is negative. Obviously, this is negative, but the problem with lambda 2 could be positive, right? So if r is large enough, right? In fact, r equals 1 looks like makes this lambda 2 0. So the real part of lambda 2, well, there's not even a real part because this are real. So if r is positive or greater than 1, let me say greater than 1, then lambda 2 is positive. So this means that E0 is unstable. Okay? Well, this conclusion is actually tells you very little about the whole system, right? It just says that if I start somewhere close to the origin with my initial conditions, I'm not gonna approach that the zero solution, right? So we can start with something very close, even, well, I don't know. I'm just picking some values, but you can see that it would be very hard to actually find initial conditions for which everything goes to zero, right? On the contrary, almost everything you put for initial conditions will actually looks like eventually is going to do the same thing that you saw earlier in some form or another, right? So, and as I said last time, that there is the better way of seeing this, right? In which, I mean, simply viewing the what is this? Simply viewing the trace of this solution, not necessarily the temporal dependence of the components, but just the trace of the solution, shows that it looks like every initial condition, well, that one can try would actually eventually have this behavior. Now, this is for this particular values for the parameters, right? But if you change the parameter, so if r is let's try 1. I don't know what 1 will do, but okay, you see the change. It's a drastic change in the parameter, right? That's for sure. But that kind of suppresses everything that was. And does it look like it goes to 0? Maybe not. But if I choose anything r that's like below 1, 0.5, then this clearly shows that it actually approaches the origin, right? Again, this this, and I'm choosing values that are very close to 0, but if I choose the original values that are far away from 0, for that change of the parameter, I forgot which value, which initial condition was here. I don't know. You still see what? That the solution goes to 0. So yes, we knew that for r less than 1, all those 3 eigenvalues are negative. So this is asymptotically stable, but that information alone doesn't tell you what happens with solutions that are, start far away from it, right? So there's a lot, a lot more that needs to be studied, to draw those conclusions. And again, here we're just kind of, experimented. I'd say, right? You see, even here, I went really far away, and I'm still getting to that. So it has to do with the dynamical system in 3 or more dimensions, which is a very peculiar feature. I mean, very, very complex. Can be very complex. Okay, but so the surprise was that there is a range of parameters that causes this kind of behavior to exist. Okay. Okay, so again, the study, what do you think the other 2 equilibria might do just from this picture? Will they be stable? You kind of see the other 2 equilibria are somewhere like where these 2 lobes are, right? And of course the origin, I rotated it, but it's somewhere here, right? So this certainly is unstable. And what do you think is happening with these 2? They'll also be unstable, right? But again, that alone doesn't explain this. So this steady state and stability of the steady state is kind of an epsilon step towards understanding this kind of long-time behavior. Okay?
I have a question.
Please.
If you start your initial conditions inside that limit cycle, you assume it'll look like the RLC, since those are unstable. They'll kind of go out into that limit cycle and look like that picture.
There is no limits. That's a good point. We would have to kind of compute those eigenvalues. Excuse me. We have to compute those steady states and start close to those to see. But you see, this is not a limit cycle like in the RLC of Van der Pol. So in other words, you cannot expect the solution to just kind of circle around this thing. It will still do the whole while, the butterfly effect. So even if you start here, in fact, I'm pretty sure that if you start anywhere in a, reasonable box, in 3D, you will always go towards this, right? So this is like an object that attracts everything, right? But this is not a closed, like there's no solution that starts somewhere, does a million things of this, and then goes back to the same place, right? So you could zoom in. This is not a best way to do it, but you could zoom in. It's like the Saturn, ring. I mean, you can. The closer and closer you go, the more things you start seeing interesting, right? Is that you actually visit the same region infinitely often, right? If you long infinitely amount of time, but yeah. And so if you start inside of that region, you will not only circle this lobe. You'll do the same dance around both lobes. Now there are two other things that I want to. I mean, there are since the discovery of this, and by the way, Lawrence made this discovery in the 60s. There's a fairly recent lecture that is videotaped, and I wanted to find it, but I couldn't. I'll put the link here, in which you can actually see him talk about these things. But last time I saw, he actually died in 2008. So just a little bit more than a year ago. But since then, there's been a huge amount of examples of this kind of behavior for in continuous time dynamical system. So one is this called Rossler attractor. So I put a link here to a Scolopedia article, and remember Scolopedia again is kind of these are actually peer-reviewed articles, and the authors are most of them are the ones that actually originated. So this is actually written by Otto Rossler. And look at the system. Isn't that amazing? It actually looks simpler than the Lorentz attractor. I mean Lorentz model. It is still nonlinear. It has z times x, but actually the nonlinearity only occurs in one of the equations. Previously, it was occurring in two of the three equations. All right, and this is how the attractor looks like. And again, for certain values of the parameter, right? So I don't know if you can see that. Okay, so the values of the parameters are written down here. Okay, so you can kind of look through this if you want. Again, looks like it has only 2 fixed points, right? And what else? I think both of them, are unstable, right? And this is kind of the geometry of that. It's in 3D, right? So it's not. It's something you can actually, build or put your hand on. Okay, so you can try this with ODE solve. You can try this if you're curious, but you will see, you'll get this picture. Okay. Let's see. So what do I want to say about this? So okay, I don't want to say much because it's very similar in a way. And it's actually even simpler to study. But what I want to point is there is actually a very kind of natural system that one that one can play with, and that's double pendulum. So I put a link to actually the other course where we talk about this in more detail on this double pendulum. So there are a few animations. Let's see. There's actually a derivation of the equations of motion of a double pendulum. So what you have is you have a pendulum, right? Nonlinear pendulum, and then attached to it another nonlinear pendulum. So this one is, obviously it has how many degrees of freedom? Okay, maybe. So what I'm referring to, how many variables do you have to state to identify to determine the state of the system? 4, right? You need its position and the angular momentum. Aren't they called? So to me, that's.
I thought you meant literally the degrees theta 1 and theta 2.
Right. So how many? Do you call those degrees of freedom? I don't know. Maybe in other fields you don't. But so I'd say it has 4 degrees of freedom. So you have 4 different 4 state variables, right? And these are the equations. Okay. Now, when I'm saying nonlinear pendulum, I'm not saying that the pendulum is like bent, right? I'm just saying that the motion is occurring not just near the equilibrium, right? So it actually can be as wildly as going around the clock for each of the pendulum, right? So for one single pendulum, you saw the nonlinear equation was what? It was theta double prime. That was the angle. Newton's law, right? Was you had the right hand side something with sine of theta, right? That made it nonlinear. And of course, if theta was small, sine of theta was approximately theta, so it made it linear. But so here you see a bunch of sines, cosines, cosine square of the differences, right? And also it involves the the first derivative, and this, I believe, ignores friction. So even in the absence of friction, you have terms with a momentum square. With a momentum, right? With a velocity square. Okay. Well, okay. So this is not actually working, but I want to show you those two equations. And you probably have seen this. Well, you may have seen it actually even in reality. Come on. But you can, if you follow, and by the way, this is not plotting in the phase space, right? It's not a four-dimensional plot. It's only a plot of the theta 1 versus theta 2, but not even theta 1 versus theta 2 is how the actual configuration of the pendulum looks like, right? But if you were to plot theta 1 versus theta 2, then it would still look like a messy, right? Unpredictable motion, right? Deterministic, but right, there's no random factors that is causing like this rotation or that, that turn or that, right? So this is deterministic, but unpredictable or sensitive to initial condition. Of course, if you are to move it, right, just a little bit, things are gonna, oops, I don't know, I'm not supposed to force it, but this just seems to, wow, okay. Now it has its mind of its own. So there was another animation which I found, but again, this you can. Oh yeah. So this is actually the plot of the angle 1 versus angle 2, but it's not. Again, it's not the phase space plot, right? Because phase space is four-dimensional, right? So this picture is what? Is a projection of a four-dimensional curve, right? In the two dimensions. Now this doesn't actually look chaotic, right? Why not? Because the initial conditions were very close to the equilibria, so this is not. But the moment you change that, and I guess you clear the graph, the moment you're kind of moving in the nonlinear regime, right? Well,
One pendulum is connected to the other. It's tied together.
well, try it. I mean, there's movies. I mean, physics people like this a lot. They make it, and then you can see that. But again, keep in mind what chaotic means. And of course, unpredictability is one thing, right? So in other words, you never kind of know how many, I don't know, revolution either will do at any time, right? But also the more important thing is that you change the initial condition by a little bit and it's going to do something totally different. Okay? Yeah.
If you have it like higher than 180 degrees, like it seems that I think this in class where if you just drop a ball up above like 180 degrees, that's chaotic, but it's not, then it's not.
Yeah, I don't think there is. There's only a limited amount of mathematical theory that you can actually apply to predict the ranges of initial conditions where things will do things and things won't do it. So, like this one, right? I mean, there are certain regions in the phase space which is four-dimensional, right? There are some pockets where there's no chaotic behavior, right? But the point is that there is. So I don't know what those pockets are. I mean, it's four-dimensional, but
On this particular example, it seemed to be stable for a little while. And then
exactly. So that's
it's lost. No, it's completely chaotic.
and by the way, you can actually do this again with your. Granted you have the time, you can actually convince yourself that this is not like artifact. I mean, this is not just a fake, right? This is simply kind of plotting the solutions of those thetas, of those values of theta, and the velocities, right, at all times. Now, are those equations always matching the experiments? No, because in experiments you have friction, you have even more complicated things, right? So, in experiments, things eventually were gonna settle down, right? Because your energy is lost through friction. But here it's, except that thing, this is actually as close to reality as you can tell. Okay, so the last thing was to actually show you that if you import this, well, import in ODE solve. So I wrote that code. Yeah, well, anybody can write it based on those equations. Okay, but and you can go to ODE solve and load the system. Okay. Now, it's a mess, right? But it's explicit, right? You can write it down. So this is, and then you can plot this. And again, the point is to plot. You see, in this case, it would really have to be x1 and x2. You can try other things, of course, but okay. And this is what comes out for this initial conditions, which are not the most probably. So you have to. I think that's what you refer to. That we actually try this with various initial conditions. I think if we choose y1 and y2 equals 0, this means the initial velocity is 0. So you always just place the initial configuration at rest at some point. But if you change those, you can see this. Yeah.
When you're working with something like this, those equations are so complex, and if you mistype a sign or a variable, something like that, is there a technique for finding your mistake, or is it just the limit?
It's like you're asking when you type on a URL in a browser and it's wrong, is there something that tells you you're wrong? No. I mean, I'm amazed how many times I mistype Google, and sometimes it just, Google says it's not, So, I don't know. I mean, looks like typing is something that still relies on us, yeah. Of course, if you see a behavior that's totally different than what you expect, well, which this is, but for domesticated models where you know what you should expect, then that's a way of checking. But okay, any questions on this? So this is chaotic behavior, of course, in 4 dimensions. But if there wasn't 3 dimensions, I mean, now it's like no surprise. This is happening in more dimensions, right? Still, I think this is much more tangible than the Lorentz model, right? Even though that was 3-dimensional, this is a pendulum you can actually manufacture and see. Okay. So, where's my? Okay. So. No. Okay. So anyway, so that was kind of what I wanted to go through. So similarly, E plus, E minus turn out to be stable, but the main point is the phase space analysis is key to long-time behavior. In nonlinear systems. Okay. 3 or more dimension, especially. Okay. I mean, even in 2 dimensions. Even in 2 dimensions. Just looking at the steady states, limit cycles, you cannot actually conclude what happens with every solution, long-term behavior. But it's much well, the possibilities are much more restricted than in 3 dimensions or more. Okay, so. So again, this is pretty much what we can do at this point. If you really want to dive into the why this, I mean, how can you explain this in kind of at a deeper level? I suggest, as I said this last time, I gave you that chapter from this book, and you can just see for the logistic equation how I forgot, it was in chapter 3, logistic equation, where you can actually write things explicitly. Even when you have chaotic behavior, you can write the iteration explicitly to see why there is that kind of behavior, or how can you explain this. But it involves, somewhat more complicated concepts from analysis. So it's a little bit beyond this class. And by the way, there's a little section in the same chapter 3 in this book, following that discussion of chaotic behavior, that talks about kind of an experimental setup where this chaotic behavior was observed in I think a bacteria population, or in some sort of population model. So it's not just that we discretize a continuous model for our convenience or for our numerical integration purposes, and we observe this thing, and it's wow, right? So it actually happens in biological in population dynamics too. So anyway, kind of interesting, and then it has pointers to more more in-depth studies of this. Okay, so let's see. I'm kind of ready to, unless you want to talk a little bit more about this, I'm ready to go to chapter 7. Start talking about probability. How many of you had probability course? I mean, okay. Well, you're supposed to have one. So, okay. So we're not going to be using a lot of hard concepts, probabilistic concepts, but models. And so again, most of things that we're going to be talking is going to be self-contained, but you should try to make connections with what you've seen before. And again, why are we adding this aspect to the to a modeling course? Well, simply because many times when we make simplifying assumptions, we ignore random random changes or random external effects on our model. So and so we until now everything was deterministic, right? We said we know how the rate of change of a certain quantity is depending on current state, previous state, whatever, right? It was very well, it was sort of very explicit, right? So let's see. So in this chapter, we're going to talk about two types. One is discrete probability models, and continuous probability model. Now, the word discrete and continuous actually has a different meaning than, well, somewhat different meaning than until now. Until now, we talked about discrete in time or continuous in time, right? So if the variables depend or change continuously or not with respect to the time. Okay, so let's see, what does it mean in this context, discrete? So we started discrete probability models. Well, clearly that experiment of throwing dice is on everybody's mind when we talk about discrete probability models. So let's just think about this experiment of throwing two dice and record the outcome. Okay, so possible outcomes are as follows. You could have numbers 1, 1, numbers 1, 2, numbers up to 6, 6 appearing on top, right? So this forms a set, right? Which, from now on we're going to talk the sample space. Whoops. You're supposed to look upside down now. The sample space. Okay, and it simply consists of, literally of this values, right? So you can think of them as some discrete set. Okay, so it's a discrete set of possible outcomes.
So can you say that because the sample space consists of a finite number of possible outcomes, it's a discrete probability model, and it's
Sure. Well, even if it's not finite, even if it's infinite, it could still be discrete, right? The point is that right. But so the question is, what would be a continuous probability modeling?
Like the normal distribution.
You would have to have the sample space to be continuous, right? In some sense, whether it's space or it's other things, but it should be kind of you should be able to move in that space continuously, right? Yeah.
Discrete is countable, continuous not countable, so the probability of anything in a continuous case of a single point.
Yeah, I'm thinking that it could also be uncountable, or no?
I don't know.
Yeah, probably not. Probably you want to stay countable.
Yeah, you can have an infinite countable set.
Uncountable?
Infinite countable.
Yeah, of course you can have infinite countable, but can you have an infinite uncountable set and still be discrete? I don't know.
Wouldn't that be like the real numbers, and then you can't count those?
Well, there are other types of uncountable sets, but anyway, it's a good thing to imagine that I can count these numbers, right? And I can list them. Countable set means you can list them, even if it's infinite. You can list it, find a listing of that. So yeah. So what happened here? Oh, it's coming up. Let me save this before it's. Okay. So just a little bit of terminology. So I wanna kind of write this down so we Again, with your experience, prior experience, and we can speak the same language. So an event A is just simply a subset of the sample space. Okay? So again, thinking of it as a finite or discrete sample space, if I only take a subset of this and I call this A, then this is actually called that I'm calling this an event, right? And I can give it a name. And of course, how many subsets? I mean, what kind of subsets can you have? Well, you can have the empty set. This would be the impossible event. At the other extreme, you could have the whole set, right? This would be certain event. Okay? So, what is probability of an event? So once you kind of say choose your favorite subset of this sample space, you can assign a probability to this event. Okay? So if every outcome in S has equal probability of occurring, then the probability of an event A is simply given by a count, right? So we write P of A to be, and that's the number of outcomes in A divided by the number of possible outcomes. So if it is a finite set, it would simply be the ratio of the size, right? The size of the subset A divided by the size of the whole set. But again, if the set is infinite, then you don't have that, right? And again, it's important that this count, that each outcome in this set has the same probability, or it's equally likely, right? So this is a determination you have to make prior to talking about probability of an event. You have to talk about probability of an outcome, okay, from occurring. So, all right. So those you probably know. So, for example, what's the probability that the sum of the two dice? What's the plural? Is it die? The two die is it dice? Okay, thank you. Is like 8, right? So when you say what's the probability that some event is occurring, it actually means count the outcomes in that event, or the favorable event, outcomes, right? So these are all the possibilities. Now, I think there's one issue here is like, do we count 2 and 6 and 6 and 2 as two different outcomes? And the answer is, well, I think it should be, right? Because the two dice have their own independent, they're not attached to each other. So one could be red, one could be blue. So if the red comes 2 and the blue comes 6, that's a different event than if the red comes 6 and the blue comes 2. Something like that, right? So in that sense, I have the probability of this event is going to be 5 over the total possibility, which is 36. By the way, should we count 4 and 4 as two different ones? No, right? So you don't, because that's just, just one outcome, right? So all of these are equally equally likely to occur, right? Each die is fair, something like that. Okay, so the next thing, which is kind of the most yes, please.
Aren't there two separate ways that 4 and 4 can happen though? Could you go into that just a little bit?
You could have red 4 and blue 4. Oh, no, wait, but
Then you have blue
This?
I don't know. I mean, look, these are questions that you have to ask. Yeah. But how come there are two different ways? Yeah. So again,
It depends on whether or not order matters.
Yeah.
If order matters, then you have to count it. If order doesn't matter, then
what order? I'm just throwing two dice.
whether you can. if you have a blue and a red die, if you have a blue and a red die, and order matters, and you always count blue first, then you're going to have 2 4s, or two different combinations of 4, because order matters, because blue is always first.
Yeah.
No, look, I'm not a probabilist, okay? So all I'm thinking is just what I think it's true. But I think it can be, formalized to the answer is that's just one event, equally likely from the other ones, okay? But I just want to introduce one more thing before we leave, and that is random variables. To me, the concept of random variables, well, of course, this is kind of the key in all probability, right? And with enough kind of exposure to it, is no longer anything mysterious, shouldn't be anything mysterious, right? Because it simply is a function. So when I say that x is a random variable, all we mean is that x is called a random variable if x is simply a function with some properties, with some additional properties, which I'm not listing here. I mean, it has to be measurable. So, but again, if S is like a finite or discrete set, all of that is thrown out of the window. It's just simply a function. So you make an assignment, and by the way, this is a real valued random variable, right? So you assign to every outcome a real number, right? And think about S as being discrete. So S is finite or countable or whatever discrete means, right? This is think about it as discrete. Okay. So for example, here are a few examples. So sum of 2 dice that is a random variable. So if I'm calling the 2 dice the red and the blue, whatever, right? So the red and the blue each goes between 1 and 6. And by the way, we oftentimes will use omega maybe, or that's customary to use omega as a possible outcome. So x of omega or x of RB, which is as a sum of the two. that is a random variable. Okay? And it's just a function. Okay? So x can take different values anywhere between 2 and 12 for this one, right? This for this example, right? Each with different probability. So when in the simplest cases, in this simple example, the question of what values can the random variable take says, is it possible, for instance, that the random variable takes the value 8? Well, if that's happening, that's an event, right? So we're looking at, this is actually an event. So the event that x is 8 is simply saying collect the outcomes in that sample space for which the value of the random variable is 8, right? So this is a subset, it's an event, right? And what's the probability of this event? Oftentimes we just ignore the accolades, so it's just say, what's the probability that this event occurs? Well, it's just counting things, and we said, right, it's 5 over 36. Okay? So in that sense, we say that the random variable can take different values with each with a certain probability. Okay? So if you do, so similarly, for instance, what's the probability that the random variable takes the value 1? Well, that's the probability of the null event, or of the impossible event. And by that count, just by the count, it says 0, right? There's no favorable outcome. So what we do here, we actually write, well, it's a kind of a midpoint to do this for every single value, but you can see that the value 2, there's going to be some probability, right? So the event, is when both are 1 and 1, and again that's one occurrence, 1 over 36, and so forth, right? Probability that x is 3 is now 2 over 36, because you can have 1, 2, and 2, 1. Yeah.
So, you have to then define what x is, like do the problem x is the sum of the two values.
Yeah. Right. So I mean, how do the random variables show up? Well, you have to make an observable. So it's whatever you observe beyond just the outcomes. So based on the outcomes, you have to make a measurement, right? In this case, it would be the sum of those two things. But whatever measurement you make, you assign a value to that outcome, right? And that's like a one run of that experiment.
So x is defined, like initially, the sum of the two x.
Yeah. So it's again, yeah. So I think that's kind of well, as part of the modeling process, you have to determine what are you observing, what are you besides just the experiment, right? But yeah, it's kind of early on in the process, certainly. So what I'm doing here is simply I'm saying that I'm looking at all possible values. In fact, it doesn't even have to be like 1, 2, 3. It could be 2.5, right? You could say, what's the probability that x takes that value? Obviously 0, right? So in this case, there's going to be just a discrete number of possible outcomes. So you're going to have discrete values for x, and those values are with 2 to 12, and with this probability. So this computation is simply building kind of the probability distribution, if you want, of that random variable, and it's just kind of writing it on, displaying it as a histogram. So histogram is basically saying how many possible, so let me put it, the probability distribution. Either way you want to look at it, it basically says the values between 2 and 12 are the possible values with what probability? Well, this is probability 1 over 36. The next one is 2 over 36. Right? And so forth. I think you're going to have the maximum, well, you have to figure out basically what the maximum probability is going to be. I think when you only have 7, that's 6 over 36. So 7 is kind of in the middle, right? The 8, which we computed, was 5 over 36. And then it comes back down to 1 over 36, right? Okay, so it's obviously it's not it's not any sort of curve like this, but you have this distribution of this probability distribution of this random variable, right? So this is sort of what we like to do with any random variable that we're given, right? So the distribution of x is given by these numbers, which are the probability that x takes value k, and k goes between 2 and, well, it could actually start with 1, right? The only thing is when k is 1, that's 0, right? Okay, so there are other things, but we're out of time. So we're going to continue this on Wednesday. If you are really bored because you've had this, I would say, you can look at this, the chapter in the book. There's not much. So we're very quickly go to continuous models, talk about the density function and all this. And I don't know. Again, you shouldn't be bored because you have to do on the other homework, which is okay. But use this as a kind of a review if you want. Okay. Thank you.